Now let's move on and look at some integral rules. So we've got our first rule, which you kind of already intuitively may know how to do. But it's going to be easier for you to test if you know this algorithm. And I've called it the reverse power rule. It's integral rule 1 in the textbook. And for any a not equal to -1, that's going to be a special case. A equals 1 is a special case, and we'll actually talk about it in just a few slides. So for any a not equal to -1, if you want to integrate a power function, x to the power of a, you are going to set the denominator to a plus 1, and then you're going to add, right? There's the adding 1 to the exponent. And so really this is the reverse power rule. So take whatever is the exponent is, add 1 to it, put it in the denominator, and then add 1 to the exponent. Here is a question. Try and apply that rule to this example. I'll give you a few moments, press pause, and then press play when you're ready. But I really strongly recommend you try it right now at home. Try using that rule. You sit on the exam, you got a time limit. Know the rule. Don't try and just figure it out as you go. That'll take too much time. You're more likely to make a mistake. All right, so I want to integrate this thing. 14x to the 6 dx. Now, the 14 multiplicative constant, that's going to stay there. I haven't talked about it yet, but I'll formalize that a little bit later. In this case, a is equal to 6. So I want 6 plus 1 in my denominator. And then I've got x to the power of 6, x to the power of a plus 1. Wow, that's going to be 6 plus 1. Gives me 14 over 7, x to the 7. And then that's going to be equal to 2, x to the power of 7. Now here's our special case. We've got a is equal to -1. This is the special case that we were avoiding before. What does this look like? We've got 1 over x. We've got x to the -1 here. If we're trying to integrate 1 to the -x, or I've got it written over here as 1 over x, remember that the log of x, we have, well, maybe I'll do it. If we had f of x is equal to the log of f, f prime of x was equal to 1 over x. And so here we've got the reverse natural log rule. And if we see 1 over x, we want to differentiate it. We're going to get the log of x. Of course, it's the absolute value. Why? Log negative is undefined. If we have log of x, x must be greater than 0. And it can't be equal to 0 either. Right? I should also add log 0 is also undefined. So here's our very specific example, right? This is a special case. And so you tell me, what's the integral, what's the antiderivative of x to the power of -1 dx? Well, hopefully you remember from the previous slide that this is just equal to the log of x, because the derivative of log of x over x is just equal to 1 over x. Now, integral rule 3, our reverse natural exponent. So remember, if we had something like EAX, and I wanted to find the derivative of this thing with respect to x, I get the derivative of the natural exponent with respect to its exponent is itself. And then I want to use the chain rule, in this case, to bring the a down. So there's a chain rule because this thing up here, we've got g of x could be equal to a of x. So we have to use the chain rule. What about if we want to go the other way? So we want to go this way. We want to integrate. We want to find the antiderivative. Well, we've got a rule right here. We're going to take this a term, that's a multiplicative constant in the exponent, and we're going to bring it and put it into the denominator. And here's a very simple example. What's the integral of this thing? Well, I know that its derivative is going to be equal to EAXA. So if I want to integrate this thing, and I just want to get e to the power of ax, that a goes into the denominator, and I get e to the power of ax. If I wanted to take the derivative with respect to x of EAX, I would get 1 over a e to the ax times a. Which is equal to e to the ax. Good so far? Not too tricky right now. Everything's moving in the opposite direction. If you concentrate, you can get to the right answer, assuming that you've already mastered the derivative rules we looked at in Chapter 6 and then applied in Chapter 7 and applied again in Chapter 8. Now there's 2 more, maybe 3 more rules that I want to share with you. The first one we've already kind of seen. If I've got the integral of 4 f of x dx, well, if I've got a multiplicative constant like 4, I can rewrite that as 4 multiplied by the integral of f of x, or the antiderivative. Formally, we could write it like this, a, where a is a constant. It doesn't have to be positive. Maybe I'll take that out and just say a is some constant. Some constant real number. And if we've got a f of x dx, well, that's just going to be equal to a times the integral of f of x dx. And a is not allowed to be equal to 0. Our next rule says that I have the integral of, say, x squared plus log of x. So I've got the integral of these two functions. I can say that the integral of a sum is equal to the sum of the integrals. And so I could rewrite this as x squared dx plus the integral log x dx. And very formally, it would look something like this. I've got f of x plus, say, g of x, d of x, and that's going to be equal to the sum of the integrals. My last rule has to do with differentiating. Suppose I write, I want to find the integral of x squared dx, and I know that this is equal to, say, x cubed divided by 3. If I take the derivative of both sides, I'm going to get d over dx times the integral of x squared dx is equal to, taking the derivative x cubed over 3, that's going to be equal to x squared. And so we've got the change in this function with respect to x, our derivative, and we've got the integral sign right here, and so the derivative and integral cancel out, and so we'd be left with x squared is equal to x squared. A little more formally, I could have written this as, suppose I have the integral little f of x dx. We know that that's going to be equal to big f of x. little f of x is the derivative of big F of x. So the integral of little f of x with respect to x is going to give us this big F of x back. And if we took the derivative of this, we would see that we get d over dx multiplied or beside the integral dx is just going to be equal to f of x. And we get, f of x is equal to f of x. So note that the derivative we are taking here is with respect to x. Also, we are considering an indefinite integral. With definite integrals in the next video, I'll just say you need to pay a little more attention to the problem setup. In practice, this means, i.e., you need to read the question carefully. So we'll talk more about that. Notice here, we're taking the derivative with respect to x. We've got a little function of x, and the integral and the derivative cancel each other out. If there might be some special situations, though, when we've got definite integrals, where it's going to be a little bit different. And we'll talk about that soon. Take a look at these questions. Try them yourself. Work through them. Press pause on your video. Give yourself a couple of minutes. Then when you're ready, press play and we'll work through them together. Let's take a look at A. So we want to take the integral of this thing, or we want to find the integral of this thing. And I'm going to use one of or sort of what I call the reverse power rule. And I can take it and write, well, one thing I could do if I wished, I could take the 2 out of the integral. It's a multiplicative constant, so I don't have to worry about it. Now, if I apply the rule to the integral part, I'm going to have x minus 5 plus 1 divided by negative 5 plus 1. And that's going all multiplied by 2. So I'm going to get 2x to the negative 4 divided by negative 4. And I can rewrite this nicely as negative 1 over x, 2x to the 4. Now looking at B, we can rewrite B as the integral. Oh, that's a very S-shaped integral. Try that one more time. And I can take the 2/3 out if I want. X minus 1 plus, dx, plus, I can take the 1 over 3 out. Right, put my integral sign, e 3x dx. So I can rewrite it like that. The first one, I've got x to the power of negative 1. That's the special case. What has a derivative of 1 over x? Well, the natural log has a derivative of 1 over x. So I can write this first one as 2/3 log x move over to the next one. I've got 1 over 3 times, what's the rule we're going to use for the natural exponent? Well, I've got the derivative itself, and I divide it by just 3. Since it's not changing, or I should say the exponent's not changing, so I don't need to add 1 like I did with the reverse power rule. And I can simplify this a little bit and rewrite it as, well, I guess there's a few things I could do. I could write it as 6 log x plus e 3x over 9. So that's where I found the common denominator. So I'd have to multiply this and this both by 3. And then I've got 3 by 3 over here, which is giving me the 9 to start with. And the common denominator of this expression is 9.